All right, so we're talking about 16.2, which is integrals on curves. And there's two categories of things that we've been working on that we're going to be studying here. The first is what we call scalar valued functions. Scalar valued functions means, oh yeah, that was it. All right, scalar valued functions means that you have a function f that takes in a point for an input and produces a number as an output, a scalar. So f of x and y is equal to z, for example, would be a scalar valued function. Scalar valued functions can be integrated using path integrals. So when we integrate a function f ds, the interpretation of this, so that we did this last time, this was called the path integral. It had a calculation formula that came with it that said that it was equal to the integral from a to b of f of r of t dt. Oh, times, I guess I should say not dt. There was a magnitude of r prime of t here. And our interpretation of that object was that this was either the area of a fence, sort of the twisty fence picture that I drew, where you have a curve and a function sitting on top of it, and you've got sort of a bendy fence, and you're calculating the area of that. Or if you think about f as representing a density, density times length would be equal to mass, and so this would be like the mass of a wire, would be another way of interpreting these integrals, right? So as mass given some density. So what we're going to do next is we're going to build this same picture for vector valued integrals, or vector valued functions, which is to say, we're going to start with a vector valued function. We're going to define an integral of a vector valued function over a path, subject to a very specific interpretation, which is going to motivate it. So we use the area of a fence to build what we thought this should be. We're going to use a different picture for vector valued functions. So our functions now are going to look like f of x and y is equal to f1 of x and y, f2 of x and y. So we eat a point and we spit out a vector. And we're going to define something called a line integral. The terminology is kind of dumb because they're not over a line, they're still over a path, but they're called line integrals. I'm going to write down the formula and then I'm going to justify it, and then we're going to derive what the calculation formula should be. So we're going to have this object f dotted with ds, but now this is a vector. So that has to be a vector for this dot product to make sense. We're going to have a vector version of ds. And this thing that we're going to build today is called the line integral. I'm not going to show you what the calculation formula is yet, but the interpretation, the core interpretation that we're going to take for our vector fields, integrals of vector fields, our line integrals, is going to be work done by some force field, F, on a particle traveling on the path r of t. So work is going to be our justification for how we build this. And so we're going to build this parallel picture for vector fields today. Okay, I did get some questions about an interpretation last time, which I thought was important to write down here. So when I write something like f of r of t, if I wrote something down like r of t is equal to t, say cosine t, sine t, t, and I write down f of r of t, so let's say f of xyz, little f of xyz is equal to x squared plus, or x squared yz. And I write f of r of t, I could write this as f of x of t, y of t, z of t. because I'm thinking of r of t as being equal to a function x of t, y of t, z of t. What I mean by f of r of t, there was some confusion in the earlier class about what x of t, y of t, and z of t actually mean, how to compute this thing. And the idea of the composition is that everywhere I see an x, I just replace it with the x value from the curve. This is going to be x, and this is going to be y, and this is going to be z. So when I write f of r of t in this picture, I mean f of everywhere there was an x, put a cosine of t, everywhere there was a y, put a sine of t, everywhere there's a z, put a t, cosine t squared, sine t, t. You're just composing the path into the function. So since that came up in the last class, I thought I would clarify if this is a point of confusion for anybody. This is how this composition works. Okay. So what we're going to do today was motivated originally by physics ideas, and it's built specifically to model the motion of particles through force fields acting on them. If you want an analogy to keep in mind here, you could think about a charged particle moving in an electric field, or a massy particle moving in a gravitational field, and what we're computing is the work done to do that over a path that is not necessarily a straight line. So that's the analogy I want you to keep in mind. All right, so we're going to start with the idea of work. Okay, so imagine that you're learning about work for the first time. Baby's first work. And somebody asks you the formula for work. And they write down W. What is supposed to go on the other side? The dumbest possible version of this. FD. You don't even say the words that they correspond to. You probably in your head just W equals FD. Okay, now really what you meant when you wrote that down, really what you meant was, the more sophisticated way of thinking about that is, it is the magnitude of the force vector times the magnitude of the displacement vector, where you have taken an object and you have moved it with some displacement d, and you've applied a force F to the object. They're both vectors, but since everything points the same direction, you just multiply the magnitudes. That is what W is equal to FD means. The magnitude of the displacement vector times the magnitude of the force vector. Work wouldn't be very interesting if every scenario looked like that. And so when you get into your college physics classes, you start doing things where they say, oh, well, what if they don't point the same direction? What if you have an object and you have a displacement that's not now it's an R2 displacement or an R3 displacement. So there's some vector describing how you're traversing that's not just in a line, and the force that you're going to apply to that thing is not parallel to it. Now how do you calculate the work done? As the object moves with displacement d subject to the force F. Okay. Work is equal to F dot d, which some of you will have learned this is the best way to do it. And others of you have learned something like F d cosine of theta, depending on the instructor and the class that you've had, right? But F d cosine theta, which is the magnitude of F times the magnitude of d times the cosine of theta, that is literally the dot product of F and d. From the vector picture, I'm going to write this down just because we learn all this vector mathematics and then nobody tells you probably that this is what you're actually doing. All you're doing here is projecting the force vector onto the displacement vector. So if you remember back in 143 when we did vector projections, if you took that picture that I drew there and you said, how much of the force vector is pointing in the direction of displacement? I mean, I want to turn this picture into this one. Well, to do that, if I drew the amount of force that was in that direction, all the free body diagram people in the classroom right now, oh God, free body diagrams. I'm not calculating normal forces or anything right now. The vector that represents the amount of force pointing in the direction of displacement is the projection of the force vector onto the displacement vector. And we have a formula for that. Now, I know it's been a long time, but I'm going to ask. If I asked you to write down the formula for the projection of the force vector onto the displacement vector, could you do it? Tell me what it is. F dot D over, okay, I'm going to write it with magnitude squared instead, if that's okay. And then actually I might go one step further and sort this into F dot D over D, the magnitude of D, times the unit vector D over the magnitude of D, if that's okay. Okay, what is the magnitude of that vector? How big is it? No. Just looking at this picture, the force vector points in the direction of the displacement vector. That's a unit vector in the direction of the displacement vector. So I've got a unit vector times a number. What's the magnitude of that? It's this thing, right? This is exactly the magnitude. This is the magnitude. Possibly with a negative sign, but it's the magnitude, right? So the magnitude of that projection, the F from our formula, work is equal to FD. The magnitude of the force vector is F dot D divided by the magnitude of D. And the magnitude of the displacement vector is the magnitude of the displacement vector. And then the magnitudes cancel. And you get work is equal to F dot D. That's why that formula is true. It's just vector projection. Okay, then the reason that you want to think about projection as being involved here is because there are scenarios when we're calculating these things that you can extract the answer just by understanding that what you're doing is projecting force onto a displacement vector. So for example, if for some reason somebody asked you to calculate, I've got a displacement vector that goes this way, and I have an object, and I have a force that was acting on the object in this direction, how much work was done by the force field on the object being displaced along that vector? Nothing. It didn't do anything, right? It contributed nothing to the displacement in this direction. That force did no work. And the reason is F dot D is 0. These are perpendicular. The dot product of perpendicular vectors is nothing. There is no projection of F onto the displacement vector. All right, so that's our basic framework. The way that this works mathematically and physically is we complicate things one step at a time. The first thing we did was say, okay, what if force and displacement don't point the same direction? And the next thing I'm going to say is, what if the displacement isn't linear? What if instead of having a straight line displacement, I have a curve that's describing how the object is traveling instead of just a line? So that picture looks like this. Now I'm going to have some kind of R of t, those are position vectors. And I'm going to think of the particle traveling along the path. And these are going to be given, I'm just going to pick some points here. Maybe that's R at a point ti, and that's R at a point ti plus 1. So I picked some t values, I've selected some points. And the idea is I'm going to also have a force field F. This is a force field, which just means a vector field. And I'm going to attach to each point on that curve a force vector. That's F, and then maybe there's an F here, and there's an F here, and there's an F here. And this specific F is the force vector at the point R of ti. This will be the force vector at R of ti plus 1. To each point on the curve, F attaches a vector. It's the point of a force field. So I would like to, this is a typical calculus move. I have this thing that works really nice if everything is on straight lines. This formula for calculating work, if everything was straight. Now things are not straight anymore, but I bet I could make them straight. So I'm just going to link everything with straight lines. I'm going to say, okay, well, I could break that curve down into bits that look like this. And those are straight line segments. They're pretty close to the curve. They're not exactly the curve, but they're pretty close. And what I'd like to do is isolate one of these pictures, like this one. Actually, I put the TIs in a different frame. So I'm going to isolate this window right here. And what I'm going to claim is, if I could figure out how to calculate the work in this little frame that I've built, this little window where I've isolated things, that looks an awful lot like a force applied to something, right? The force is going in this direction, and the curve is going in this direction. Maybe I can use this formula to figure out what the work is in that little window. Now, previously, we've talked about breaking a curve up into little pieces of arc length, delta S. But I can't calculate work from a force vector dotted with a scalar function. Length is scalar. I can't use a scalar function. I've got to use a vector somehow to calculate displacement. So I'm not interested in distance. I'm interested in displacement. Can I use the information I've got here to produce a vector that points from here to here? Like starts at this point right here and goes like that. What would it be?
R of ti plus 1 minus r of ti.
So we're going to call that vector delta S with a hat on it, I. It's the displacement chunk, not a distance chunk. It's not an arc length chunk. It's a displacement chunk. And we're going to define it to be r of ti plus 1 minus r of ti. That is a vector quantity. Every one of these will have a vector quantity attached to it. Every one of these has a delta S. That's the vector that points from here to here, the vector that points from here to here, the vector that points from here to here, and so on. So I can break the curve up into a bunch of vectors that crawl through the curve. Okay, if that's delta Si, if this vector right here is delta Si, vector quantity, how much is the work done in that little frame right there? If the particle traveled from this point to that one with that displacement vector, subject to that force, what would the work be? Okay, so we're going to call that little work. Little work. Little work is equal to the force field at that specific point dotted with the displacement vector at that specific point. That's just F dot D. Work is equal to F dot D. What if I wanted to know the work on the whole curve? What would I do? Sum them all up, right? That's about, so we're doing the classic calculus move now, where eventually I'm just going to assert that a limit happens and then an integral falls out the bottom, right? So now we're going to say, so big work is the sum over all those pieces I decomposed the curve up into. So if I added up the work done on this frame, plus the work done on this frame, plus the work done on this one, plus the work done on this one, and I added them all, I would get an approximation for the total work. So I guess we should say approximately equal to here. So work is approximately equal to the sum over I of F of R of Ti dotted with delta Si. And if I let those little vectors get smaller and smaller, that is, if I broke this into smaller and smaller pieces, this approximation would get better and better. The more of the little pieces I break the curve into, the better my approximation of the work is going to get. So this is kind of you'll have to see it in a later class to prove it, but now what we're going to do is we're going to let the size of those vector pieces go to 0. So as I make the vectors shorter, what happens is we get what we want to be our definition. So we are taking this as a physically motivated definition. Work, this is a definition, is equal to the integral over the curve of the vector field dotted with ds. So when I write down a line, this structure, I am thinking of this as a force vector dotted with a little tiny vector, so it is work that I'm calculating here. I'm adding up a bunch of little tiny work units. Of course, the problem is I didn't tell you how to compute it. This is an awesome symbolic move, right? We've used all this geometry and vector mathematics to write down what we think it should be. Geometrically, this should be what our integral is defined to be. But I'm going to have to come up with a way of actually writing down something you can do. All right, so I'm going to observe the following. When we wrote down the integral of f ds with a scalar ds over r, we replace this with the integral from a to b of f evaluated on the curve times the length of r prime of t dt, which is to say, scalar ds was the length of r prime of t dt. Now, in a completely unjustified way, I'm going to ask you to guess what vector ds should be equal to.
The dx dy.
No. This is a scalar. This is a scalar quantity, right? Scalar ds means I took the derivative and took its scalar magnitude and multiplied it by dt. Get rid of the absolute values. R prime of t dt. I'm going to justify this in a second. This looks like magic, right? Because I've just asserted that this is true. But scalar ds is computed with the magnitude of the velocity vector. Vector ds is the velocity vector. So why should that be the case? Why should we intuitively believe that? It's that you're saying a little tiny bit of displacement is your velocity vector times a little tiny bit of time. That is displacement. Displacement is equal to velocity times time. Velocity is a vector now, not a scalar quantity. So that's a velocity. That's a time. So your tiny bit of displacement is your velocity at a point times a little tiny bit of time. A more theoretical justification for that move is as follows. We are basically making the following argument. That if, that should make that curve way shorter. So imagine that you got really close to the curve r of t. And you calculated this vector, which is the displacement vector delta s. So that vector points from that point to this one. I'm going to write down a calculation. If I took r of ti plus 1 and I subtracted r of ti from it, in fact, let's do it this way, this is even more clear. R of ti plus delta t minus r of ti. That's how you get from ti to ti plus 1, right? Is you add a little bit of time. And then you notice that is delta s right there, right? This quantity is delta s. The distance from the previous point to the next point for the current one. This dude right here, that guy is delta s. Now, when I see a difference like that, because I've taught a lot of calculus, I just instantly want to divide it by delta t. Because now it's a difference quotient. And if I took the limit as delta t went to 0, what would that be equal to? Looks an awful lot like the derivative, right? Wouldn't that be the definition? Isn't that just the definition of the derivative at ti? Okay, so here's your power move, applied mathematician engineering thing. I could get rid of the limit, and then I just put it almost equals right here. For sufficiently small values of t, that's true. But now, since they're approximately equal and there's no limit, if I want to chuck delta t over to the other side, I'm allowed to do that. Now it's just algebra. I mean, obviously, about equals is algebraically stable, right? So multiply both sides of this not inequality by delta t, and you end up with r of ti plus delta t minus r of ti is about equal to r prime at ti times delta t. And what we're saying is, if I calculate my velocity at a particular position, and then I multiply by a small amount of time, the vector of my displacement based on my instantaneous velocity is about equal to what I actually did. The reason that this limit turns out to be equal is because the function is assumed to be differentiable. If you make smaller and smaller pieces, these arrows get closer and closer together. That's essentially what we're saying here, is that delta S is approximately equal to R prime at Ti delta T. And if that's not enough for you and you want some more meat, way back in one of your classes, you probably learned about a mysterious theorem called the mean value theorem that nobody even told you why you learned it. It was just taught to you as, oh, this is a really important theorem, and then you either did nothing with it or some really stupid examples where you like found some slope of some function that was equal to the slope between the endpoints, right? The reason that this all works is because the mean value theorem is true. I can only do this because of the mean value theorem. Now, I'm going to wave my hands just as much as the earlier classes and say I can't show you why, but the idea of replacing a difference quotient with a derivative, difference quotients being able to be approximated by derivatives, is the content of the mean value theorem. So, if you want to see why this is true at a higher level of generality, I invite you to join me in Math 413 the next time I teach it. It was our second course in theoretical real analysis. All right, so that's an awful lot of abstract theory. And the point is, when you're done with it, what you get is the computational formula for this. The integral from a to b of f of r of t dotted with r prime of t dt. That is our computational formula for line integrals. Okay, so all of this bloviating aside, what do you actually need to know? So the work interpretation is important. We're going to say the following. So given a vector field F and a path R of t, the line integral of F over R is defined to be the integral over R of f dot ds, vector ds, and the computational formula for it is ab f of r of t dotted with r prime of t dt. This is the core of our conversation right now. And then off to the side, we'll say, we interpret this to be work. So I'm going to give you an example. And we'll see if we can use geometry to figure out the answer, and then we'll verify with calculus. Here's an example. Let's let our vector field F be equal to xy. And let's let the path be cosine of t sine t. And I want the work done by F on a particle traveling along R of t. So, in a lot of these problems, when you have the ability to do so, you can actually draw this. And you should. Here's the path. This is R of t. I guess I should tell you some bounds here. T goes from 0 to 2 pi. So I have a particle traveling along that path. What the force field is doing along that path at any point, x of t, y of t, the force field is producing a vector. And we're thinking about that force as acting on the particle. So now, without doing any calculus at all, can you tell me the answer to the question? Why? Because the force is perpendicular to the direction of motion. So without doing calculus, you could look at this and say, if the particle is traveling along the path in this direction, at any particular point, it looks like it's traveling in the direction of its derivative. And the way I've set this up, the derivative vector and the force vector are orthogonal to each other. The projection of the force vector onto the velocity vector is 0. Yep.
Even if it wasn't perpendicular, don't because we end in the same place work out.
Okay, so you're anticipating a theorem about conservative vector fields. I haven't talked about conservative vector fields yet. It is not the case that every vector field is going to get you back to where you started with 0.
How can that physically be possible?
Because there's non-conservative vector fields, basically. So if conservation law is active, all that matters is you're starting and ending position. So gravity is a conservative vector field. Electric fields are conservative. But there's physical fields that you can build up that are non-conservative. There could be things happening. So like in fluid dynamics, a lot of times the description of velocities of fluids are not conservative. So it very much matters which trajectory you take. And you can go around in one direction and end where you started and have done work by going around in different paths. Even on a closed loop, you can induce work that way. So yeah, if there's any rotation in the vector field at all, it's you don't have that property. We're gonna get into the theorem that says that. It's a good insight. So for the most useful vector fields, yes. Ending up where you started, we're gonna go into detail on that. Right? In this case, even if I'd only done a half circle, say, the answer would still be 0 here. If you liked it better, let's do this. I can make it from 0 to pi. Now I'm not ending where I started. I started here and I ended here. I'm not looping. I can put a pi here, so we avoid all questions about ending where you started. So I've now not walked from the top of the Empire State Building to the bottom and then back up again. Is the answer still 0? Yeah, at any point, the force and the motion are still perpendicular to each other. So the projection of the force vector onto the the velocity vector is 0. There is no projection. If you actually compute this with the formula, you would get the following. So let's verify that with calculus. We think the work should be 0. Let's verify. F is equal to xy. R is equal to cosine t sine t. The integral on R of f dot ds should be equal to the integral from 0 to pi of f with r plugged into it. So that's cosine of t sine t. This is f of r of t. Dotted with r prime of t. Well, r is cosine t. So that's the worst cosine. Which is going to be minus the sine of t cosine of t. That quantity right there is r prime of t. And if you calculate that dot product, what you end up with is the integral from 0 to pi of cosine times minus sine plus sine times cosine. And that's the integral from 0 to pi of 0 dt, which is 0. It's precisely what we anticipated. Yep.
Why are the force vectors pointing out instead of inwards?
In this particular case, remember, we're not thinking about this as being acted on. We're not thinking about forces due to the forces that must be present in order to keep this thing traveling on the path. We're talking about an external force field acting on a particle that must be, if we know that the particle is traveling along this path, right? And there's and I have some force field that's acting like this. So one way of thinking about this might be, what would be a good physical analogy here?
Is it traveling on that path with the force?
Imagine that you had some sort of a charged particle here that was, the problem is that the vectors are pointing in the wrong direction. This is not really a physical example because the vector field that you get here gets bigger the further away that you get. But the idea is, if I just told you that the particle is traveling this path, and it was inside this vector field, the answer would be the vector field has nothing to do with the physics that the particle is experiencing, right? The work done by the vector field on this particular path is nothing. I could set up a particle to move along this path without having to introduce external forces to keep it on that path. It can move freely along this path with no additional force because the vector field is doing no work, right? So it's like the vector field applies nothing to the particle. Like in a gravitational field, for example, I'm going to get off my skis here, so I'm going to stop, right? But the idea here is because the path is perpendicular to, okay, if I pick up a bag of sand and I walk along the floor with it and the floor is horizontal, gravity's done nothing. The potential gravitational energy of the bag of the sand is the same no matter where I walk horizontally, right? So the gravitation, even though there was work involved, the work that the gravitational field did to increase or decrease the potential energy of the bag of sand was zero. It's the same height relative to the floor no matter where I walk. That's what we're saying here, is that like the particular gravitational field does no work. It's not introducing or taking away any potential energy into the system. Yeah. Okay, other questions about this? All right, so let's do another example. And I'll end by talking about path independence a little bit, or independence of parameterization. So the last example I want to talk about today looks like this. Let's take a look at the integral over c of x squared dx minus xy dy plus dz, where c is the part of the parabola z is equal to x squared, y is equal to 0 from the point -1, 0, 1 to the point 1, 0, 1. Okay, so we have this path. Path looks like this. Here's x, here's y, here's z. It's a parabola because the y values are all 0, and it goes from the point 1, 0, 1, and then it's parabolic. It's stuck in the. Oh, I'm going the wrong direction. It's in the xz plane, isn't it? So it goes like this. From here, it sort of loops down to 0, 0, 0, and then comes back out the other side to that point. So that's the point 1, 0, 1, and that's the point -1, 0, 1, and we're supposed to start this point and then travel the curve this way until we end up here. So that's our path C. What's F in this problem, the way that I've written this down?
X squared minus xy 1.
Yeah, so F is x squared minus xy1, because this is the differential form of a vector field. F1 dx minus F2 dy plus F3 dz. Of course, the problem is that's an integral over a curve, not an integral over a parametrized curve or a path. How am I going to get a parameterization in this thing? I need an R. I need an R of t. I'm going to take the easy one. I bet y is equal to 0. What's the relationship between, if only I had an independent variable? What should I set? What should I let my independent variable be? Z or x? You guys like square roots, huh? All right. If z was t, that would mean, so if z was t, then also it would mean that x squared was equal to t, and so root x would be, or so x would be equal to root t. Ugh, roots. How about we choose x to be t, and then z will be t squared? That's probably a better way to do it, unless you like square roots. Like, I'm not going to stop you. Right. So that is a way of describing traveling along this parabola, because y is equal to 0, and whatever the x values are, the z values are the squares of that. What are the t's that go with this? Parameterizations don't mean anything without beginning and end points. So I need some t values. So if I was going to set up this integral subject to these pieces, I know that I'm looking at the integral over c of f dot ds. Hopefully, that's equal to the integral from -1 to 1 of f of r of t dotted with r prime of t dt, which should be the integral from -1 to 1. Okay, so f of r of t is t squared 0, 1. X squared is t squared, xy is t times 0, which is 0, z is equal to 1, dotted with the derivative of r, which is 1, 0, 2t dt. And then you could proceed to finish the integral. So this is f of r of t, and this is r prime of t. A question you might have here, though, a natural question is, what if I had picked a different way to parameterize that path? That's not unique. There's lots of ways to parameterize a path. If I set something up like this up, I picked a parameterization of the path. I could pick a different one. I could do it twice as fast or half as fast. I could replace all the t's with 2 t's and then let t go from -1/2 to 1/2, and I would get the same curve. Does choosing a different parameterization change the value of the integral? Is a real question. So, one way to think about what should happen, what your expectation should be is, if I have my bag of sand, I'll go back to the Empire State Building again. If I got a bag of sand and I carry it from the bottom of the Empire State Building to the top, from the standpoint of the gravitational field, did it matter how fast I did that? If I sprint versus if I go like 1 step an hour, the total potential energy that was added is the same. The work done by the field is the same. What if I did it in the other direction? What if I have the same path, but I started at the top and I went to the bottom? I should get the negative of going up, right? Work should be reversed because I was traveling with the field instead of against it. So the theorem here, my concern is, if I had picked a different way of traversing this curve, does the answer turn out to be the same? And the answer is yes, as long as I did it in the same direction. If I had done it in the opposite direction, the answer would have been the negative of my original answer. If the integral, so we'd say if R1 and R2 parameterize the same curve in the same direction. The fancy mathematical word for that is orientation. If the curves have the same orientation. Then the integral over R1 of f dot ds is equal to the integral over R2 of f dot ds. That's called independence of parameterization. It does not matter how I chose to do that as long as I'm starting at the same position in both things and ending in the same position in both things. If they're opposite, if R1 and R3, say, parameterize the same curve in opposite directions, the fancy word for this is reversed orientation. Then the integral on R1 of f dot ds is equal to minus the integral on R2 of f dot ds. Do the path backwards, get opposite work. This is a theorem you already know from Calculus 1 because you already know the integral from a to b of f dx is equal to minus the integral from b to a of f dx dx. If you reverse the order of integration, you stick in a negative, it's the same theorem, but in All right, that's it for the day. Next time, what we'll talk about is one thing that we have not talked about yet is, this is where Thomas is driving at here, is if I go from the bottom of the Empire State Building to the top and I come back to where I started, I have added no energy to the system, right? There's no potential energy. The work should be zero. On any closed path, in certain kinds of physically meaningful vector fields, the only thing that matters is displacement, where I started and where I ended. So we're going to talk about gradient fields, which are the fields that have that property. They have what are called path-independent line integrals. And then we'll talk about checking to see if a vector field is a gradient field, which says when you know that you only care about where you finished and where you begin. All right, see you guys next time. Oh, tomorrow we're doing a mock test.